Yes.
Okay. Okay.
All right.
Awesome.
Okay.
Perfect. Thank you guys for being patient. We are finally ready. So we are very happy to have food for counseling here visiting us. So no more delay. You have 1 full hour.
Thank you. All right. Good. So thank you very, very much for the invitation. So as the title suggests, I'm going to be talking about finite temperature quantum topological order in 3D. This is work that is done in collaboration with Shitong Zhao, Meng Cheng at Yale University, Tyler Ellison, who was at Yale University, but has moved to Purdue, and my old collaborator, Tibor Rakowski, who's in Budapest now. All right. So I thought maybe I would start with a summary of what this talk is generally about. So actually, as a rough show of hands, who sort of knows what topological order is? Has seen a few models before. Okay, all right, fine. Good. So some of you might have heard this result before, that without active error correction, topological phases are in some sense unstable at any finite temperature, at least in sufficiently low dimensions. So what that means is that if you took something, a canonically topologically ordered state like the 2D toric code, or something like the fractional quantum model, yes?
We'll do something in the top. Is everything fine? Maybe
I'm not able to access the chat
Okay,
because,
so-
yeah.
If anybody wants to say something from the chat, just raise your voice. Maybe.
Right. Okay, so there's this general idea that topological phases are thought to be unstable at finite temperature in basically physical numbers of dimensions. D is equal to 2 or D is equal to 3. And I'll explain a little bit why people think that in a second. But this is the sort of general expectation that we have. And so the punchline of this talk is that it's not actually true, and there's actually quite a simple model in 3 spatial dimensions, which retains some vestige of topological order at finite temperature. This model will be called the fermionic toric code. And I'll also give you a sketch just now as to where this is going to come from. It turns out that this fermionic toric code, so you look at it at finite temperature, which means you take this Hamiltonian called the fermionic toric code Hamiltonian, and you look at its Gibbs ensemble, e to the minus beta h, right? And it's the properties of this Gibbs ensemble that we're going to be interested in. And the point about this Gibbs ensemble is that it has a very special symmetry, which is only sustainable in a system that has topological order and interesting kinds of quantum entanglement. And that symmetry is called the fermionic loop symmetry. So basically, and there are some epsilons and things in these equations, which I'm not writing down, but the long story short, this density matrix, this thermal density matrix has a specific symmetry. You take the density matrix and you act on the left of it with some string of operators. That's what this equation represents, okay? The density matrix is fixed under that operation, okay? So it has this, something that we call a line symmetry, and people who are very sophisticated about these things would call this a two-form symmetry, okay? So any one of these loops, you can draw any loop you like, any closed loop you like, the density matrix is fixed under this operation. But it turns out that that loop has a very special property, which is if you break the loop open and get a line which has some endpoints, then those endpoints have fermionic statistics, okay? And this is a very special thing because it turns out that this fermionic toric code model is a model of qubits on the lattice. There aren't any fermions or anything anywhere in the system. So basically, this is a system that has a kind of emergent fermion. You started with bosons at the microscopic level, and somehow fermions emerged out of the system. And it turns out that having such an emergent fermionic line symmetry is incompatible with having a trivial unentangled state. And it's in that way that we think that this state is topologically. That's the sort of broad picture. Yes.
Has this gone beyond the normal toric code yet?
Is this true in the normal toric?
I mean, you have emergent fermions in the toric code as well, right?
In the 2D toric code?
Yeah.
Yes, so I'll explain what happens in that case. So at finite temperature in that case, both the vortices and the particles proliferate, and you're unable to define a symmetry of this form. because basically the
so-
background fluxes will interfere with this fermionic operator, whereas in 3D, well, you've stolen my thunder now, so I'll just explain. I'll explain what happens when I get there, but yeah, I'll get to that in a second. Any other questions? Because I realized this first bit was maybe a little bit rushed and garbled.
I'm sorry to interrupt, but we can't see the full screen.
I see.
We can see the first 3 bullet points, but the diagram is cut off on the right.
Okay. Not totally sure what to do about that. Is this any better?
No.
That's right.
Well, we can see, maybe if you zoom out further.
Any better now?
Um,
I'm gonna stop sharing and then share again and see if it helps. I was sharing the window.
If you have a screen, it might work. It might be.
Oh, I see. Okay.
It might recognize the full screen, it's the same thing.
Yeah, okay. Share. What do I say? Application.
Entire screen.
Where is entire? Entire screen. Okay, fine. Okay. And then I come here and whoops. Now I can't. There you go. Is this any better?
yeah, that's fixed it. Thank you so much.
Sorry, I can.
That's good. Thanks.
That's good. Okay. We have this slightly annoying you are sharing screen thing.
If you go to it, hover over it.
Yeah, I can't. There's no mouse is the thing. Like for some reason, I think it's because I'm plugged into the.
Go out of full screen.
Oh, the full screen. Okay.
Oh.
Yes. Now put it up here.
Go to more.
More. Yeah.
Fine. Or is that high?
Down to.
More.
Hide floating meeting controls. Okay. And people online, does this still work? People online?
Yeah,
Hello?
that
Yeah.
works. Thanks.
Okay, good. All right, thanks. Okay, so the first bit was maybe a bit garbled for various reasons, but any sort of questions about what's generally going to happen? There's this Hamiltonian in 3D. Its ground state is definitely topologically ordered. And the point is that there is a regime at low, but non-zero temperatures where it is in some sense still topologically ordered.
Sorry, can I ask?
Yes.
Just something in general with this problem. So why you consider the Gibbs states? Like why are you guaranteed to have the sum state is this Gibbs state?
Why is the Gibbs state a natural thing to consider?
Like no, why the sum state is a Gibbs state in this case?
I mean, that's the definition of a Gibbs state, meeting minus beta h.
No, but I understand that, but you are not, for example, you may have other symmetry constraints coming from I don't know, other like higher form, such that you like the Gibbs, like the sum state is not in this particular form.
Oh, you're saying that in a system that has a number of higher form symmetries, the system might not equilibrate,
Exactly.
and for that reason, the Gibbs state might not be appropriate?
Yeah. I'm just saying why you make this assumption.
It seems like a natural enough assumption to think that the system will come to equilibrium with the Hamilton, with a Gibbs state meeting minus beta h. But what you said is reasonable. There will be some other quasi-static states which correspond to other topological sectors. But
Yeah, for example, it's not only like toric.
yeah,
If you have like one form symmetry, there are many observables that's not summarized. But anyway, it's not.
But that's the point, right?
Uh-huh.
That's what you're protecting. That's the part you want to be not fertilizing.
so what do you mean by there are many observables that do not thermalize? I don't understand what you mean by that.
No, it's some reasonable code. So you have it's pretty particle with one form symmetry.
Yes.
And if you do some observable for this one form symmetry thing, it like the thermal average is not the Gibbs, it's not the Gibbs of thermal average.
How do you define the thermal average?
Like I can say.
Yeah, but that's true because it's the models that we tend to use for this tend to be integral and they're exactly we choose models that are exactly solvable. So that's just the statement that the eigenstates of the stabilized Hamiltonian are not representative of Gibbs ensemble. On the other hand, if I was to literally take this toric Hamiltonian and couple it to a thermal bath and allow it to equilibrate, this would be the appropriate state to look at. So I say that this is the more natural thing to look at.
Yeah, I agree, but do you have a proof or something like why this?
I mean, I can prove to you that there exists open system dynamics which have this as a steady state and which can reasonably be thought of as I've coupled the toric code to the thermal bar at temperature T and the toric code thermalized to the steady state.
Yeah, I mean, I don't have a problem with it. It's just in general, like there are many works, for example, consider such. I just don't know the general philosophy of why like people. Okay, sorry.
Maybe I don't really understand the question. This is an appropriate state to look at if you couple the toric code to the thermal bath without it.
Yeah, yes, yes,
Which I think is a well motivated physical question, because typically the system that we're looking at is not that some sort of bar.
yeah, yes, for this I also agree. I agree this is.
But
I'm just asking, are there more like rigorous justification for this kind of physical idea?
A more rigorous justification that systems that are coupled to thermal baths come towards a given state.
Yes, but especially when you have some like special like other kind of symmetries.
I mean, that's like,
I mean, right.
if the system is coupled everywhere to a thermal bath, I don't think that those things are so important, actually.
I would suggest you can continue.
Okay.
Yeah, sorry.
Okay, all right. So, what do I mean by topological phase? For those of us who, well, if you come from a stat mech background or a more traditional condensed matter background, then the way that we think about, let's just talk about phases. We think about phases as being regions of parameter space where the properties of a material or a system are basically continuous. You know, we have some parameter regime where we're ferromagnets or something, we have some other parameter regime where we're a very exotic phase diagram, where we have a superconductor, and there are maybe sudden changes in the partition function or correlation functions across a phase transition, but there are sort of these regions of stability, and that's what we think of as being a phase. There's a somewhat more newfangled definition of a phase, which sort of operationally the same as this existing one in the case where we talk about ground states. And it basically characterizes phases in terms of the ground state wave function. And it says that two ground state wave functions are in different phases, basically if it's difficult to get between those ground state wave functions by doing local operations on the system. Okay. Another way of saying that is that basically ground state wave functions that are in the same phase differ by, roughly speaking, a local change of basis. But things that are in different phases differ by highly non-local changes of basis. The sort of language that we use to describe this is in terms of depths of circuits. So if you imagine psi and psi primed are two wave functions, we'd say that they're in the same phase. If you can get psi primed from psi by acting with a low depth circuit. Each one of these bricks is like basically a two-site interacting unitary gate, right? So basically, if you can get between these with a low depth circuit, low depth means that the number of layers here does not grow quickly with system size. It grows at worst logarithmically. That's the sort of definition of phase. Okay. Okay, so I just mentioned that because those ideas are going to be somewhat important when I try and define what I even mean by topological order at finite temperature, because even that is in some ways a vexed question. So in order to define topological order in this density matrix setting, I'm going to define it by defining what it isn't. So I'm going to define something that's trivial, and then I'm going to say everything that isn't trivial, we're going to say topological. Okay, that's the way around we do it. And there might be a more sensible definition of topological order at finite temperature. I think this is still an area of active work, but this is a definition that others have adopted, and it's the one that we'll use here. Okay. So in order to define topological, I'm going to say what it isn't. So I'm going to say that something isn't topological if it looks like the following. Call it road trip. I'm going to say a density matrix isn't topological if you can form it by doing the following. You take some trivial short-range entangled product states. So you start with a product state, you do a few operations on it. That's what each of these psi i's. And you do some diagonal combination of those. So almost some classical probability distribution over those diagonals. Anything of that form, I will say, is trivial, topologically trivial. I'll add a little bit extra, which is I'll also allow you to do some low depth channel on top of this mixture. That will also be trivial. So this is what we mean by trivial state. here is an archetypal trivial state. There are various examples of trivial states. One would be just a simple pure state where all the spins are in the zero state. But another would be, according to this definition of trivial, something like all zero plus a projector onto all zeros plus a projector onto all ups, something that looks almost like a classical fermionic. That is also considered to be topologically trivial in this language. Yes.
Right, so I'm not sure I understand this. Surely, like any given solids has a mixture.
No. For example, because the Hamiltonian can contain terms that are off diagonal.
Oh, in a particular basis.
Yeah,
Okay.
like basically
Okay,
the Hamiltonian is certainly diagonal in the energy eigenbasis. The question is whether or not it's diagonal in like a computational basis or some local basis.
Okay.
Yeah,
In
that's,
general use.
that's more than a purification. I mean, as written there, it is like a purification or a density matrix, but you're saying more.
Yeah,
Okay, yeah.
Okay.
So you mix specific computational basis here for those.
You see, it's sort of in the no, I'm not picking a specific. The reason it isn't is because I didn't quite say how to define the psi I. Here's any of those psi I's can be of the following form. Take product state of computational basis, hit it with any low step circuit, including one that changes the local computational vector. So that is so it's actually this statement is actually independent of that basis because you can do arbitrary changes of the on-site basis during that operation. Okay. So basically, these are things that are easily obtained from product state.
There's some notion of locality that's kind of built in there, or
Yes, the psi I is a short range entangled, by which I mean, if we reference the previous page, they're of this form where the input state is product state. That's what the psi I is. Okay, so what we're the sort of goal that we're aiming at is to show that this fermionic toric Gibbs state is far from any trivial state. And that's what we're going to show. So in particular, we can show that the fidelity between the fermionic toric code and the trivial state is tiny. And this is actually more or less equivalent to saying that the norm difference between the density matrix is large as it can be.
Any trivial state.
Any trivial state.
So it is an optimization in that expression.
Yes, any trivial state. Basically, the point is that any trivial state can't have this weird fermionic line symmetry, and that allows you to construct a variable or an observable where these two things differ. And this one norm, it actually has a nice operational meaning. It tells you what the largest possible difference in an observable error in an observable is, in a bounded observable. And so this ends up fine, very far away from each other. Okay. Any questions about that? All right. Good. Okay. So let's actually just talk about, things will slow down now for a little bit. We'll just talk about some traditional toric codes, like simple topological orders, and I'll introduce the model one step at a time, okay? So we're first of all going to talk about a well-known 2D topological order, and we're going to talk about why it isn't stable at finite temperature, okay? And then I'll contrast that with the 3 fermionic toric code and explain why it is stable at finite temperature, and that's sufficiently stable at finite temperature. So here's the toric code. This is actually this sort of, you can see this is copied. I got a bit nostalgic. The very first talk I gave at a conference, I did this slide in Beamer, and I was feeling a bit nostalgic, so I thought I'd use it again because it was very close to my heart. But anyway, so 2D toric code, probably you've seen it on the square lattice before. Here I've decided to put on the hexagonal lattice. So there's a spin, a qubit on every bond of this lattice. That's what each of those dots are. When the spin is pointing up, so sigma z is up, I'll color the bond in. When it's pointing down, I won't. Okay. There are some flip spins along the line of that. The toric code has 2 sorts of terms in its Hamiltonian. It has a vertex term and a Plaquette term. These are all stabilizers, which means that each of them is a product of Pauli matrices. All of these operators that occur in the Hamiltonian commute with one another, and this allows you to solve the Hamiltonian. Okay. So the BV term, let's just go through this. This is the vertex term. It acts in the following way. You go to a vertex and you hit each of the edges with sigma z. And so this term will be +1 if there are an even number of line segments coming into the vertex, and it'll be -1 otherwise. And so you see that in this Hamiltonian, we'd like to maximize BV. The biggest it can be is 1. BV is equal to 1 means that these loops don't have any endpoints, closed loops. Right, so our ground state ends up actually having closed loops in it because you can independently minimize the terms in this Hamiltonian because they all commute with each other. Okay, all right. So this tells us that they're closed loops. The other type of term called the plaquette term, you go to a plaquette, you look at all of the edges that surround the plaquette, and you flip them with a sigma x. Okay, so if you were to act on this configuration, for example, with a BP, there's some segment of loop coming in here. If you act on this with BP, you flip this plaquette, which basically has the effect of popping the string over the plaquette. If there was no string there, it would create a loop out of nowhere. Okay. Now, this part's a little trickier to see, but it's also true, is that if you want to minimize the Hamiltonian, you set all the BP's equal to 1. And what this forces you to do is to superpose all possible loop configurations. Basically, if one loop configuration occurs in the ground state, then any loop configuration you could obtain by flipping a plaquette also affects the ground state the same ways. Okay, so you can solve this exactly. I've already sort of said this. You set all the BVs equal to 1, all of the BPs equal to 1, and you can just write down what the ground states look like. Okay, so I'll do that. This is I'm doing this on the torus, so periodic boundary conditions in both directions. You in fact get 4 possible ground states. One of the ground states, the first ground state has an even number of loops winding system in each direction. Okay. And you can see that within that sector, you allow yourself all possible plaquette flips. And the point is that if you flip these plaquettes, you're not able to get between sectors that have different winding numbers. And that's the reason that this system sort of that the ground states end up being 4 orthogonal different states, because you can't get between any of these even winding sectors and any of the odd winding sectors by flipping plaquettes. Okay. All right, so you get 4 different ground states. For those of you who are interested, this is basically the model that's used in many of the quantum simulation experiments we have to store quantum information. So it's the surface code is used in IBM Google's devices, for example. And the way that you store quantum information with this sort of state is you store it in basically your bit ends up becoming 0 if there are an even number of things winding the torus in one of the directions, and 1 if there's an odd number of things winding the torus in that direction. And it's in that sort of delocalized degree of freedom that you encode your quantum information. And it's the fact that it's sort of delocalized. And it's a very non-local question, right? Asking, do an even or an odd number of loops wind the system? You can't just tell that by looking at a small patch of the system. And it's precisely that delocalization of this information that protects it from noise in quantum simulators. Okay. So another thing about this model, and it's closely connected to the statement about ground state degeneracy, is that there are 2 types of excitations in the model above the ground state. There are these things that we call vertex excitations and things that we call plaquette excitations. And from the name, you can sort of guess what they are. Vertex excitations are points where the vertex operators are unhappy. Plaquette operators are where the plaquette operators are. Plaquette excitations are where the plaquettes are unhappy. And you should basically think about these as being the vertex excitations. You can think of as being little electric charges that are tied to the end of a string. And you can form a pair of those by choosing some path on the lattice and flipping all the along that path, and that will create a pair of these excitations. And they'll have an energy that just scales like the number of particles that you've inserted, which is 2 in this case. So 2 times whatever the gap is in this case. Likewise, there are these magnetic excitations or flux excitations, which you can get by acting on a line on the dual lattice with sigma z's. And also, likewise, the energy of this excitation is just proportional to the number of these endpoints or the number of fluxes that you insert. Okay, so there are these 2 types of emergent excitations, and a really special thing about them is that, here are the operators of insert them, just the record. One's basically a string of sigma x's, one's basically a string of sigma z's. Really important thing about these operators is that, or about these objects, is that if you braid one of these blue excitations around one of the red excitations, you get a Berry phase -1. So they have a statistic, or an anionic, a mutual anionic statistic. In fact, you can sort of see how that's encoded in the operators, because you can see that if you had a line of x's and it intersects a line of z's, that those two operators will actually anti-commute, because there'll be some common edge where there's a sigma x and a sigma z acting, and those two operators anti-commute with one another. So this anionic statistic is actually encoded in this operator. Okay. All right. So another way of saying this, and this is maybe the more newfangled way of saying this, is that this state has an emergent and anomalous higher form symmetry. And what that basically means is the following. If I ignore the red particle for now, if I take the blue particle in a loop, that amounts to acting with x's along the loop. Okay, that's what that operation is. If I hit my state with that operator, I get the state back. Likewise, if I take a magnetic flux excitation in a loop, I get the state back. So these are basically symmetries of the state. These are operations that fix the state. So the point is that if you have these operations that fix the state and they have this mutual anionic statistic, where if you try and move parts of the operators through one another, you get a minus sign, it implies that the state is long-range entanglement. Okay, I haven't proven that to you, but that's something you can prove. Okay. And I was actually going to go a little bit through that argument now on the board, but I think I might hold that for the question time. Basically, the main point I'm making is that if you have this type of symmetry on a state in 2D, you can prove that it's far away from any trivial state. Okay? So it has these two types of line symmetries, and the two types of line symmetries have this anionic statistic where they anti-commute. This sort of behavior is unsupportable on a trivial state. Your state necessarily has to have some entanglement in order to have that property. And moreover, you can be like more quantitative about it. In particular, the fidelity of any state which has this set of symmetries with a trivial state is exponentially small, for example. Okay. All right, so I can talk about how that's proved later. We're basically lifting there a nice, I mean, it's been known in one form or another for a while, but there's a particularly nice proof of this statement that appeared last year, which we adopted for our work as well. Okay, so then I told you that in low dimensions, topological order dies at finite temperature, so I should tell you roughly why that happens. So basically, what happens at finite temperature? So we have this Hamiltonian, it's got the set of ground states, and we've got some point-like excitations above the ground state. Okay, so what happens when we go to finite temperature? Well, at finite temperature, you know, let's imagine what happens when I consider adding some extra particles into the system, right? So there'll be an energy cost associated with putting some extra particles in the system. It'll be, you know, order one, it'll be the gap, delta, some microscopic parameter on the Hamiltonian. When I put that in the free energy, it'll be like, you know, that over temperature. Okay, but when I think about whether it's a good idea to put those particles in, I should also take account of entropy, right? And so if I think about what entropy is associated with putting some extra particles in the system, it's log of the number of states associated with those extra particles being in the system. Each of the particles can be anywhere in the system, so this is something that's going to scale like system volume to some power. When I turn that into an entropy, I get log of system volume or log of system sum. Okay, so when I consider the free energy of adding some extra particles in the system, I have a competition between delta or beta delta and something that's log L. The log L can get big in the thermodynamic limit and it always wins. And so basically it always makes sense to proliferate these point particles everywhere. So if I try and draw a cartoon of what the a thermal state looks like, it looks sort of like this. There are basically there's a proliferation of these plaquette and vertex defects going around, and this stops you from being able to define this statistic, or like to basically these line operators. You lose the symmetry is the point. And so you can no longer say that the thermal state has these properties. There are other things you can measure as well, things like entanglement negativity, which also similarly show entanglement negativity or entanglement topological entanglement entropy, which also show that the state is no longer topological and is now trivial. Actually, there are various ways of proving that the finite temperature state is trivial, but this is maybe the intuitive way of seeing it. Okay, so that's
this.
Yes.
I mean, the argument is very simple, of course, is the mixing entropy of this point like excitations, but the statement holds as long as you have a non-zero density of these excitations. You say I can go to very low temperatures.
Yes, yes.
But then there is a little scaling limit where you can be at some
Yes, yes.
vanishing temperature
yes,
where
yes.
you have sub-extensive.
Indeed, something like this happens in quantum Hall devices.
Okay.
Because, by the same sort of argument, the fractional quantum Hall effect shouldn't exist, right?
Yeah,
But the point is that the devices are much smaller than the thermal coherence length.
okay.
Or because they're in this mesoscopic limit. So it's a story about order of limits.
Exactly.
So indeed, if you made the temperature like small in system size, like, one over L or whatever, then this is considered the calculus.
So then when you say that they use this as, in actual devices.
Yes. They use it, but they don't tend to, it depends on exactly which experiment we're talking about, but they don't tend to engineer the Hamiltonian model system down. What they tend to do is a code. So they tend to measure these operators instead. So and try and they don't actually do that, but yeah, the idea is eventually they'll try and correct the errors on the fly. Yeah. Okay. All right. So 2D topological order dies, and then the sort of intuitive picture as well, though this is maybe not really the point I'm trying to make today, is that you lose the quantum information that you stored in the winding number sectors, because all of a sudden these particles proliferate across the system, and they end up changing the winding number around the different directions of the loop, and it destroys your quantum information. So that's what that picture is supposed to say, but that's not really what I'm getting at today. Okay, so that's 2D, and so you might ask what happens in 3D. So we'll first of all talk about the very well-known 3D topological order, the 3D toric code. It'll turn out that this model is also trivial at any finite temperature. Then we'll put a little twist on the model and show that the resulting fermionic toric code is non-trivial at finite temperature. But let me first of all talk about the 3D toric code, because it has some of the properties of the fermionic toric code, but it doesn't have that extra fermionic twist in it, which allows us to say that it's non-trivial at non-zero temperature. And indeed, it has been proven to be trivial at any non-zero temperature, which was proved by Hastings a while ago. Okay, so just to get you used to 3D, we're going to work in the cubic lattice. There are spins on each edge of the cubic lattice. I'm going to use the same convention as before. When the spin's down, I'll color an edge in. When it's up, I won't. There are two types of terms in the Hamiltonian. There are vertex terms and plaquette terms. The vertex terms are active vertices, and they're products of z's on all of the bonds coming into a vertex. Vertex term being happy is again going to be equivalent to the condition that there aren't any loop endpoints in the ground state. So it's again going to be some superposition of closed loops, but this time they're in 3D rather than 2D. The plaquette terms do the same thing as they did before. They hop the loops, this time over plaquettes. So again, the Hamiltonian is exactly solvable. The ground state has all BV is equal to 1, all BP is equal to 1. So basically, once again, the ground states are going to look like this kind of loop gas, this equal sum superposition of loops. Okay? So we get something like this. And on the 3 torus, in this case, periodic boundary conditions in all 3 directions, there are 8 ground states, which correspond to the 8 possible ways that you could have a loop winding around in 3 directions. So 2 to the 3 is 8. You could also use this to store quantum information. This is what the ground states look like. Equal sum superposition of all of these loop configurations. Any questions about that? Nope. Okay, good. All right, so what are the excitations in this model? So again, we have 2 types of excitations. Excitations where vertices are unhappy, excitations where plaquettes are unhappy. So the excitations where the vertices are unhappy are pretty much the same as they were before. They're created by acting on edges on a line with some sigma, flipping some edges along the line. So sigma x's along some edges. And this operation creates point-like excitations at the endpoints of that line segment. That's what this WV operator is supposed to represent, and it's given by that green line on the right-hand side of the picture. There's a little difference here, an important difference that happens for the plaquette excitations, because it turns out that if you have you have a cube, and it has, let's say, an unhappy plaquette here, it turns out that there's a constraint between the plaquette operators. Because if you actually multiply all the plaquette operators on this cube together, it's 1. So basically, the unhappy plaquettes always come in pairs on a cube. And that ends up implying that plaquette defects always live on some closed loop on the dual lattice. So actually, they're vortex loops. rather than being point particles as they were in 2D, they're sort of these closed loops on the dual lattice of unhappy plaquettes. This will be very important because if you think about it, the energy of such an excitation will end up scaling with the size of this object. Previously, we had two plaquette defects. We move them further apart. There's no increase in energy moving them apart. Now we have this vortex line. If you want to make the vortex line bigger, it costs more energy because there are more unhappy plaquettes in the vortex line. This will be important. Another thing to note is that the vertex defects, they end up being bosonic, which is if you sort of do an exchange, if you create, let's say, two pairs of these vertex defects and you exchange a pair of them adiabatically, you'll just get back the ground state wave function. These things behave like bosonic operators. Probably obvious why I'm going to be mentioning that, because that's not going to be true in fermionic. Right. Another thing you can do is braid these vertex defects and the plaquette defects. So you can sort of create a pair of vertex defects, send them around a vortex loop and annihilate them again. You get a Berry phase of -1 from that. Maybe before. Okay.
I'm sorry.
Yes.
I need something basic. So you say that the vortex loops now depends, so the bigger ones cost more energy.
Cost more energy, yes.
So you're in confinement. So where is the topological?
No. You're thinking of point-like defects. Usually when we talk about confinement versus deconfinement, we're talking about a Wilson loop or a Wilson line operator. We're asking about the energy of that. Wilson line operator inserts a pair of point defects.
But here, what do you say?
Here, what do I mean by what?
You insert it, what difference? You insert it.
Well, you act on a surface on the dual lattice with sigma z.
Yeah.
It commutes to the Hamiltonian everywhere except at its endpoints. And there you create a line, a closed loop of unhappy plaquettes.
And the energy you say depends on the size of the loop.
Yes, because
Because they're more plaquettes.
yeah, the Hamiltonian is sum of BP, sum of BV.
So how is the loop?
The Hamiltonian is sum of B. Well, for example, the Wilson line has a perimeter law. That's our usual diagnostic for deconfinement, is that you look at a closed Wilson loop and you ask whether it has a perimeter law or an area law. This is a perimeter law. Yeah. So why does this have a linear line cost? Because remember that we minimize the Hamiltonian when we set all of BP's equal to 1. This is a line of BP's which are equal to -1. So the number of unhappy terms in the Hamiltonian is scaling like the length of this. Okay, so we're now going to do our entropic argument again and sort of ask what finite temperature state looks like. And the phase diagram here is more interesting. So at any finite non-zero temperature, the plaquette defects once again proliferate. Sorry, the vertex defects again once again proliferate for the same entropy argument for log b to 1, right? However, the plaquette excitations do not immediately proliferate.
This is what you were saying.
Right, they do not immediately proliferate. They tend to be small, the plaquette excitation. And the reason for that is there's actually a non-trivial free energy calculation to be done now, a bit like a Piles argument. If you consider this vortex loop that we're considering on the left-hand side of the board, maybe I'll be democratic and go to the right-hand side of the board. There's this vortex loop, this line of unhappy plaquettes. The energy cost of it is going like, the length of the loop. The number of loops of length L is roughly exponential in L. So that means the entropy is also going like L with some of the coefficients. And when you balance these two things together, you find that below some critical temperature, the loops will not proliferate. It doesn't make free energy sense to proliferate the loops. So the loops are short. Okay, so that means that, intuitive picture for the ground state is that there are these vertex defects everywhere. And then there are these tiny lines, these small defect lines everywhere as well. And so you might ask, yeah, okay, good. Sorry. So that's what happens at low temperature, but non-zero temperature. Then at sufficiently high temperature, everything proliferates. Because, past a certain limit, it really just does make entropic sense to proliferate the loops. Okay. So you might ask, so we know that the state is topologically ordered at T is equal to 0. Is it topologically ordered in this finite temperature regime where the loops are short? The answer turns out to be no, but it's not immediately obvious that it would be trivial. Right, I'm actually going to defer this bit to the next. Well, okay. One thing I'll say is that because the vortex loops are small in this phase, you can do some fairly simple local operations which gets rid of it. In other words, you can take your density matrix and basically do some local Garber dynamics, and it will quite quickly get rid of all of these loops. And if you do that, it turns out that this state has one of these line-like symmetries. It still has these vertex defects everywhere, but if you insert an extra particle and take it around in a loop, you find that the density matrix is invariant under that operation. So basically, what I'm saying here is that the thermal state here is close to something that has a line symmetry. Okay. Now, it turns out that that line symmetry is not interesting enough to imply that the density matrix is interesting and topological, but it will be enough to imply that it's interesting and topological in the fermionic toric code case, which is what we'll look at.
So for the boson, sorry, so
Yes.
for the bosonic case, we still have two phases, we still have a phase transition.
You have a thermodynamic phase transition here,
Yes.
but the state is not topological here.
And it's what, like higher form symmetry, something?
It has a higher form bosonic symmetry, but it's still trivial in the sense that I said at the beginning of the talk.
Okay, okay.
You can actually prove it's like one of these separable states. That's something that Hastings did.
And this
yes.
boson loop symmetry is something like the product of the sigma x operator.
Yes, exactly. Yes.
And I need to get rid of the small loops because
Yes.
there's some contributions where I don't want.
Yeah, because if there was like a small red vortex loop here and it happened to braid it, you wouldn't necessarily get back the same state, especially if there's some superposition of that vortex being there, and not that.
But it's one minus something exponentially smaller than length. Okay.
It's if you looked at the expectation value of this loop in the thermal state with the short loops, its expectation value would decay like the length of this, because there's a constant probability of it either linking a small vortex loop or not, and so you'll actually get an exponential suppression.
Right.
But the point is that you can clean up the state with some local operations in such a way that you have this exact symmetry, and it'll be enough to be able to say something like that in order to prove what we need to prove. Okay. All right. So the fermionic toric code. So I guess probably Levin and Wen were the first to write this down. I also actually ended up writing this down in my PhD thesis, which was kind of interesting to see it pop up again in this context. So the Hamiltonian looks almost the same. All right. Ignore this top equation. There's an error in there. Right. Sorry, I just copied the toric code Hamiltonian.
You have the.
Yeah. Oh. There's this. Yes. There should be some extra z's in here, okay? Not just x. And the way that you put the z's on is denoted here. Okay. Thank you. Okay. So it's got the same vertex terms. So again, we're going to want configurations of closed loops. Same story there. The plaquette terms are a bit different. You sort of flip a loop over a plaquette, but possibly with a phase, depending on what other loops are around it. Okay. Basically, you put some z's on here. I'm not going to explain how the flipping process, sort of exactly what it does, but you'll see on the next page what the effect is on the graphs. Basically, these used to be diagonal on x. Now they have some x and z stuff happening in them, and that's going to be enough to make the finite temperature state of this model special. So it's again the case that the ground states end up being a superposition of closed loop configuration. It's again the case that the 8 ground states when you have periodic boundary conditions on the torus. In fact, the ground states look almost exactly the same, but if you've got sharp eyes, you'll see that there are occasional minus signs here, which weren't there before. The idea is that whenever you have one of these loops do a kind of self-twist, so this sort of motif, you get a minus sign. Okay. This, by the way, this Hamiltonian breaks rotational symmetry, because you might well ask, well, this doesn't look like this from the side. So there's a specified direction. There's direction specified in the definition of this Hamiltonian. So, for example, this minus sign over here occurs because of this self twist that you see there. Okay. All right. And this actually tells us something like the endpoints of these lines are going to have to behave a little bit like fermions. Because, you know, if you, one of those self-twists ends up looking something like this. So if you think about that, that's like a 2 pi rotation of a fermion. And so the self-twist ends up, you know, if you do a 2 pi rotation of a fermion, you get minus the fermion back, basically. Yeah, okay. All right.
They're ribbons.
They are ribbons, yes, they are framed loops. You can think about it that way. Yeah, so actually another way of figuring out whether or not the wave function should have a sign in it is you take whatever loop configuration it is that you've been given, you shift it in our particular direction. So, you know, like sort of out of the board or something like that. I don't know, can't quite, like, I'm not going to be able to draw that. And then you ask what's the linking number of the parity of the linking number of the red and blue configurations. So it's a, you can think of it as like a framing for a Chern-Simons term, something like that. Okay, so this model again has 2 types of excitations. There are places where vertex operators are unhappy, places where plaquette operators are unhappy. The places where the plaquette operators are unhappy are actually pretty much the same. They're just vortex loops as before. The places where the and they're created by like acting with a sheet of sigma z's as they were before. And you get plaquette excitations at the edge of the sheet. The vertex operators are a little different in the sense that they're no longer created by like a line of sigma x's. You have to decorate that line of sigma x's with some sigma z's. So basically, you insert a pair of vertex defects, but in a way that sort of depends on the positions of other loops in the system. And those positions are picked up by these extra sigma z's. And so I haven't said exactly how to do that, but basically, these vertex type string operators end up inserting point particles such that when you do an exchange on a pair of those point particles, you get a -1 sign. So they behave like fermions. Okay. So the model again has point-like excitations and these line-like plaquette vortex excitations, but the point excitations are fermionic. Even though the underlying model is bosonic, it's just a model on qubits. So we say that this model has an emergent fermion. Okay. Okay, so much like you know, the toric code case, having this this electric charge and this flux line, having the symmetry. Oh yeah, sorry. One more thing, which is that if you take one of these vertex excitations in a loop on the ground state, you get back 1. That's a symmetry of the state. So basically, there's a lemma which I'm not going to go through the details of today, which says that if you have a state which has this fermionic loop-like symmetry, and it's a symmetry of the state, and when you open up the loop-like symmetry and do an exchange of the endpoints, it behaves like a fermion. That's enough to show that it's far away from any trivial state. Okay, right. It's basically states which give rise to fermions, even when they have underlying bosonic degrees of freedom, are special in some way. You want me to go through the sort of?
So that's the lemma.
That's the lemma, yeah, that's the lemma. And what I'm saying is that it's a very similar type of lemma to the perhaps more plausible one that I said before, which is that if you want to have a state which has these E particles and M particles, and they have a mutual statistic, it cannot be a trivial state. It's the same sort of thing. You basically do a kind of braiding or exchange experiment, and you show that you can only possibly get a phase from that operation if the state has a lot of entanglement in it. Entanglement, yeah. Oh, 10 minutes. Oh, sorry. I thought you were saying entanglement with emphasis. Okay, yes. Okay. No, it's fine. We're almost done. It's like, okay. So in order to show that this state is non-trivial, it's like maybe a little bit technical, but like here's the idea. So, all right, let's consider this state at finite temperature. So at 0 temperature, it's topological. At finite temperature, we're going to argue it's still topological. At high enough temperature, it would be trivial. Basically, this phase diagram looks like the phase diagram for the 3D toric code. It's the same sort of considerations. As soon as you're at a non-zero temperature, the point particles proliferate as before. As long as the temperature is low enough, the line defects, the vortex lines, don't proliferate. So they're small line defects. And it's in that phase that we're going to show, perhaps surprisingly, that this state is still in some way non-trivial. It's topological. Okay. And the idea, just sort of giving you a sort of sketch of the proof, is that we start from this finite but low temperature state. We remove the loops. we get something that has this fermionic loop symmetry. That's enough to show that this state, the cleaned up state, the state where we remove the vortex loops, is far from any product state, or far from any trivial state. And then we can sort of, there's a sort of extra technical bit that says that because this operation of removing the loops was very simple, this state up here is also very far away from any trivial state. That's the logic. Okay. Not immediately obvious that that should work. The fact that we can clean up the loops easily, I'm not going to go into, maybe you don't have enough time to go into that, but you can ask a question about it. Basically, you know, in this low temperature phase, the loops are small, right? So what's the size of the biggest loop in the system? Well, the probability of having a loop of length L in this low temperature phase is going to go something like this for a positive cathode. Okay, so so what's the longest possible loop? Well, you know, basically the probability of having a loop somewhere of length little l is going to be equal to the system volume, let's say L cubed, this thing. And then if you think a little bit about that, you can see that the largest expected loop in the system will be only of size log L. So that's what makes the loop cleaning procedure efficient. Basically, by just looking at log L patches of the system, or log L squared we used in this case, you can, there's a 5-step procedure which basically gets rid of all of the loops with essentially by probability 1. Yeah. All right. Here's how it works. Basically, we break the system up into big blocks that are of size log L squared, and then we just shift the blocks every few steps. We clean up the loops, and we're sort of done at the last step.
So what would happen if they were not longer?
If there was no, like if we were above the critical temperature, for example, there would be loops in the system that are polynomially sized in loops, in system size.
Okay.
And that would mean that we need to do very non-local operations on the system.
How does it affect the phase?
How does it affect the phases?
Yeah, there is still topological.
No, it's not topological. Yeah, at high enough temperature, it's not topological. Trivial here. Because we can't clean up the loops in that case without dramatically reconfiguring the state, and all of the lemmas fall down. Yeah, okay. As they should do. You can also prove that the high temperature state is trivial. Yeah.
But this kind of comes back to your definition of what topological phase is.
Yeah.
If you allow operations over log L.
Yes.
but
That's
not
what we tend to mean by low depth. Low depth is like up to log L. And like the basic reason for that is that you know, if I think of like a depth D circuit, and I think about what that does to operators, I can sort of grow them distance D, but perhaps with some exponential tails. And log L is like the largest distance you can get, such that when you truncate those tails, you get something that's like polynomially small in system size. You get like a tail, as so it's like an e to the minus something, and then you put a log in that position, and the actual error is like 1 over L or 1 over some polynomial in L. So that's what tends to set the log L. Yes, 5 minutes. Okay, 5 minutes. Not topological. Okay, yeah. Okay. All right. So I've already sort of gone over this bit, but basically we do the loop cleaning procedure. Our state ends up having the symmetry. I call this thing row empty set. Okay, for no loops. This thing is far away from any trivial state because it has this anomalous set of symmetries, exact symmetries. This step is not very complicated and is local, which ends up implying that, which together with the fact that this thing is non-trivial implies the original state is non-trivial. And sort of the chain of inequalities that's used is kind of just sort of put on the slide. Probably I should simplify this slightly, but yes, it's basically what I said. So the lemma that we were using is this one, which says that the state without any vortices is far from a trivial state. This comes from this fermionic exchange thought experiment I was talking about. So you can use that exchange thought experiment to say that the state without any vortex loops has a tiny fidelity with any trivial state. Then the next part you use is something called the data processing inequality, which says that the distance between the original fermionic toric code state and a trivial state is less than or equal to channel acting on each of those. That's the data processing inequality. This channel is the loop cleaning state, the loop cleaning channel. This is just the state without any loops. It's this up to some incredibly tiny error, which you don't have to worry about. So this ends up saying that the fidelity of the fermionic toric code state at finite temperature and a trivial state is less than or equal to the fidelity between this state without any loops and this channel acting on a trivial state. Now, it turns out that the channel, because it's low depth, when you act on this trivial state, gives you back another trivial state. That's an extra technical step, but it's plausible. You do something very simple to a trivial state, you get another trivial state. Okay. So we can again, so this thing ends up being bounded by some of this exponentially smaller system size, and that in turn tells us that the fidelity between the fermionic toric code state and any trivial state is exponentially smaller now, from which everything else follows. Okay. Right. Okay. So in summary, topological phases were thought to be unstable in low dimensions. We showed that at least some form of topological order is stable in this fermionic toric code model at sufficiently low temperature. The topological nature of the state followed from this fermionic loop-like symmetry, and our main contribution was to find a procedure that restored this exactly in such a way that we could show that the original thermal state was actually far away from any trivial states. One thing I didn't sort of talk about very much is that although the finite temperature state is topological in the sense that I said it's far away from any trivial state, where I defined trivial at the beginning of the talk, this fermionic toric coded finite temperature is not useful for quantum computation. Turns out you can't store any useful quantum information in that phase because you lose the relative phase information between the different topological sectors. So it's only a good classical memory, but it is non-trivial in the sense that I said. Okay, good. That's all I wanted to say. Yeah.
Thank you very much. Questions? Questions from the chat as well, if you have questions.
You never told us what this combination of X's and sets was.
Oh, for the fermionic toric code case? You mean for the plaquette operators or for the line operators?
So
Either?
So one was the same set combination. The XXX in the plaquettes got some sets.
Yes.
You never told us what that was.
Ah, yeah, okay. Let me get back the picture. So let's see. Yeah. Here it is. The plaquette operators.
Yes.
So it's X's on each of these as before.
Yes.
Then it's Z's on these blue edges.
I got it.
So it's,
I can't.
oh, you can't see that. Okay, no, that's fine. That's fine. So
the blue edges are going out.
Yeah.
No, I got you. Okay. It's just like that. It's the product of the 4X's times 2 sets.
exactly.
Okay.
And basically what these two sets do is they keep track of whether or not that plaquette flip has introduced itself first.
So, and I don't know, it's probably elementary to show that these commutes, I guess commutes. Everything commutes, and this is what brings the minus signs.
Exactly, yes.
So now second elementary question as well.
Yes.
So the ground state of the 3D is
This
just
one of the most just
the original one, the
yeah.
bosonic, let's
Yeah.
say, the toric code as well.
Yeah.
It's just all pluses.
Yes.
And the reason is that that operator is stochastic.
Sure.
So this operator is not stochastic.
Yeah, I guess not. Although maybe I don't know the definition of stochastic.
Obeys per non Frobenius, so
Yes.
it's a tilting of a stochastic operator. You know, some of us doing large deviation know about it. And that's why your ground state is not like a probability object, because you have the minus.
Yeah, I guess that must follow.
Yeah,
But
okay.
Yeah, here's the reasoning that I would use to say that it's a positive superposition in one case and not in the other.
Yeah.
So maybe let me know if that maps onto what you're saying about stochastic.
I think this is an elementary statement and
Okay.
you know, nothing deep. I think we agree.
Okay.
You don't need to prove. Yeah.
More questions?
And but it was its direction, you get the rotation, because they kind of have a certain direction where those legs.
Yes. Yeah. So for example, like you can see that this is a privileged direction, not the other way. Yes. That's baked into the Hamiltonian. Yes.
So I think, here you have this cross symmetry.
Yes,
So that doesn't
after
matter,
doing the cleaning up.
doesn't matter whether you have big or strong.
Yes,
What if I have big symmetry?
I wouldn't know how to prove the lemma in the case that we have weak symmetry.
So you must have the.
So for the proof that we have, yes, and to use the leading Yoshida result, yes. That's not strong symmetry.
Weak symmetry is exponentially decaying or
No, it's a phase.
out of the hand.
Yeah, it's like, in order to. Yeah. I'll talk about the toric case because it's simpler than the fermionic case, which is actually like the example. So what you do to show that non-trivial statistics end up implying non-triviality in the state is you basically you take your E line, take your M line, which is equal M, and you look at an observable that corresponds to the following diagram. So what this basically means is you act with sort of half of the E operator first.
Yeah.
Then you act with the M operator, then you act with the second half of the U operator second. And you're doing this on some state, right? And the point is that this should equal exactly minus that state. Okay, and it's from this, you can use this to show that this state cannot be a trivial state. It must be very entangled. It must be the result of acting with a really large depth channel on a trivial, a large depth circuit.
It was your lemma,
No, this is the Lili Yoshida lemma.
or the lemma.
Yes, the lemma, and then you can also use this to show that this state necessarily has trivial, has very small fidelity. So anyway, your question about strong symmetry versus weak symmetry. So it's like important that there's a phase here, right? So basically in trivial states, it ends up being a +1. In non-trivial states, it can be a -1. Okay. Now, in the case where you're thinking about weak symmetries sort of act on the bra and the ket space at the same time.
Okay.
And you can't get the phase.
Yeah.
So that's the reason that as it currently stands, the proof doesn't work.
More questions? Okay, also due to time, I think we should stop.
Yeah.
And then whoever wants to talk to Kurt, we will be here for a while, so you're welcome to
It's in the queue.
to put in the.